Elham is a postdoctoral fellow at the University of Alberta, and she's working with Dr. Levi Lellis, and she's focused on developing algorithms for synthesizing effective and interpretable strategies for solving problems and playing games. So she completed her PhD from University of Regina with Dr. Sandra Zillis in 2021, and his PhD research was focused on establishing trust between agents in multi-agent systems. So with this introduction, the floor is yours, Elham.
Yeah, thank you for your introduction. Let's share my screen. Okay, today I'd like to share with you guys this work that I did during my PhD. Actually, my PhD supervisor, Sandra Ziles, is here. Hello, Sandra. And the title of my work is Efficient and Robust Method for Computing Trust in Multi-Agent Systems. In multi-agent systems, agents often need to rely on resources or services provided by other agents in order to achieve their goals. So collaboration among agents can be considered an important part of multi-agent systems. For efficient cooperation, agents often have to assess one another's trustworthiness. One example can easily explain the intent of this work is an electronic marketplace. Assume you're going to buy an item from Amazon, and there are several providers that sell this item. So you as a buyer need to decide from whom you buy the item. Several factors are going into this decision. For example, the price of the item, the quality of the item, or for example, the customer service. Some of these factors are easier to assess, like the price points, as you can easily compare the dollar values from several sellers. But some other factors, like the quality of an item, might not be as trivial to assess as the price. For assessing the quality of an item, you may rely on the reputation of a seller. I mean, if it's a known brand and you had previously enjoyed its brand quality, or you may compare the reviews from people who have already bought this item from these sellers. To map this example to multi-agent systems, we can assume each entity is an agent. A buyer corresponds to a truster. Sellers are modeled as trustees, and also reviewers who provide recommendations on trustees are advisors. So here we have three types of role for agents in a system: a truster, a trustee, and an advisor. Typically, an agent's trustworthiness can be represented as a numeric value called the trust value. As I mentioned in the example, the two main sources of information to drive the trust value is our direct trust information, which is based on a truster's past experience with a trustee, and also indirect trust information, which is computed based on recommendations provided by advisors. In this domain, we have some challenges. Direct trust is not always available or reliable. For example, in a larger scale multi-agent system, or when a truster or a trustee joins a system as a new user. So we don't have any history of interaction. Also, when trustees have dynamic behavior. For instance, assume a seller has offered good services a year ago, but recently its service quality has significantly decreased. Also, indirect trust can be difficult to establish since advisors themselves could be unreliable. And you can think of scenarios like bad mouthing or ballot stuffing. The other challenge that we have here is how to combine direct and indirect trust effectively. The rest of my talk is divided into 3 parts. In the first part, I'll introduce our approach to compute indirect trust through an online learning algorithm. Then I'll talk about our broad empirical study on combining direct and indirect trust. And in the last part, I'll introduce our approach to handle dynamic trustees. Okay, let's start the first part. As I mentioned, in this part, we focus exclusively on the problem of computing indirect trust. And the goal here is to estimate the trustworthiness of trustees accurately and to minimize the number of unsuccessful interactions. Many indirect trust models have been proposed in the literature, as you can see here, for example, Travis, Habit, MET, and ACT. But we show that the simulations presented in these studies are not comprehensive enough to evaluate how well a system can handle a specific type of advisor's dishonest behavior. For example, MET claims that it can perform better than Travis based on simulations with a fixed distribution of trustee behavior. But based on our simulations, which is average over 100 random trustee behavior distributions, both methods fare equally well on average. Also, some of them cannot scale well in terms of memory and runtime, so they are not practical in larger scale multi-agent systems. And most of them are not evaluated in terms of utility-based measure. We propose ITIA indirect trust with expert advice to compute indirect trust effectively. And also it scales well, both in terms of memory and runtime. ITA is based on the prediction with expert advice strategy, as is often used in online learning. So in our framework, a truster tries to estimate the trustworthiness of trustees only based on indirect trust information when it has no history of interaction. And the only information shared by advisors is the estimates of trustworthiness of trustees. In each round, the truster receives recommendation from advisors, and then it picks one trustee to interact with. After that, it observes the outcome of that interaction, and it updates its indirect trust for that trustee. As I mentioned, ITIA computes indirect trust through an online learning algorithm. One of the fundamental settings in online learning is predicting from expert advice, or PA. The procedure of the PA model is as follows. Suppose that a learner aims to predict an unknown sequence O1 to OT of outcomes. Then in each step, the learner has access to the predictions of K experts, here denoted by F. So F sub 1t refers to the prediction made by the first expert at time step t. After that, the learner makes its own predictions using the provided recommendations. The true outcome is observed, and the learners and the experts' predictions are evaluated using a loss function. The loss function simply is the difference between the prediction and the actual outcome. In this model, the learner's goal is to minimize the regret. And regret is the difference between the learner's total loss and that of the best expert in hindsight. Intuitively, regret measures how sorry the learner is not to have followed the predictions of the best expert. Here you can see the mappings between ITIA and the PA model. A truster in ITIA corresponds to a learner in PA. And an advisor in ITIA is modeled as an expert in PA. Now let's go through the steps of the ITIA algorithm in more detail. In each round, a truster estimates the indirect trust value of each trustee using the exponential weighted average strategy. In this equation, WK is the weight of advisor K, and FK is the recommendation provided by advisor K. Note that larger weights are assigned to advisors with lower losses. So here, weights reflect the past performance of advisors in a cumulative way. So ITIA doesn't need to memorize individual losses incurred by advisors in previous rounds. And this makes ITIA efficient in terms of memory and runtime. The other point is that the weights assigned to advisors depend on a trustee, so that the system can handle advisors that are more reliable for some trustees than for others. And this is important in scenarios where some advisors want to, for example, badmouth some trustees while being truthful about some others. In the next step, the truster tries to minimize its loss by picking the trustee with the highest trustworthiness value. Then it initiates an interaction with that trustee, and the actual outcome of the interaction is observed. In the last step, the weights of advisors are adjusted depending on their losses. Here we have an exponential factor. L is the loss function, and eta is the learning rate. In our simulations, interactions with a trustee are either successful or unsuccessful, so the outcomes are binary. For each trustee, we have a constant trustworthiness value in the range of 0 and 1. So it indicates the probability that an interaction with that trustee is successful. When an honest advisor is asked to provide its recommendation on a trustee, actually it gives its own direct trust in that trustee, which is computed based on beta reputation formula. More precisely, direct trust is computed by applying the standard equation for the expected value of a beta distribution. And you can see the formula here. P is the number of past successful interactions between an advisor and a trustee, and N is the number of past unsuccessful interactions. In the previous slide, I mentioned that an honest advisor provides its own direct trust as a recommendation, but a dishonest advisor could provide the distorted version. Our evaluation contains settings which differ in how advisors can distort their actual recommendations. For example, in the bad-mouthing case, a deceptive advisor negatively distorts its recommendation. And in the ballot stuffing case, the advisor positively distorts its recommendation. We compare ITIA to the methods Travis, Habit, MET, and ACT in terms of two evaluation metrics. The first one is mean absolute error, or MAE. It refers to mean absolute difference between the actual and the estimated trustworthiness values. But MAE ignores utility aspects such as cost. If an unsuccessful interaction is more costly than a successful interaction, then MAE alone is not sufficient for assessing a method. So we evaluate the methods also in terms of relative frequency of unsuccessful interactions, or RFU. RFU is the fraction of the number of unsuccessful interactions over the total number of interactions. Based on our simulation results, in terms of RFU, ITIA, Travis, and MET are the winners. So we have studied MAE only for the RFU winners, and it turns out there is no clear winner in terms of MAE. While Travis and MET on average work as well as ITIA, neither MET nor Travis would be practical in larger scale multi-agent systems. MET's runtime is prohibitively large. It uses an evolutionary algorithm to detect honest advisors. And Travis needs to store all the past recommendations by all advisors over time, which makes it infeasible in terms of memory consumption. ITIA's memory consumption, by comparison, is negligible. Okay, let's wrap up the first part of the talk. Based on our results, it turns out the best existing methods for computing indirect trust are overly complex. The very simple method, ITIA, shows that such complexity is unnecessary for solving this problem. ITIA either outperforms or competes with all tested methods in the vast majority of the settings while scaling substantially better. We also showed the importance of studying utility-based measures. Actually, the most popular evaluation metric in the trust model literature is MAE, but I mentioned that MAE ignores utility aspects. For example, two agents may have the same MAE after the same number of total interactions, but one may have more unsuccessful interactions than the other, and thus pay higher cost. And intuitively, a system can perform many successful interactions if it can identify even a single highly trustworthy trustee. And to do so, it's not required to estimate the trustworthiness of all trustees well. In some applications like e-marketplaces, it's important to perform mostly successful interactions. And for such applications, we should put more emphasis on RFU than on MAE. And this work has been published in IJGAI 2019. Okay, in the next part, we try to answer two questions. How to combine direct and indirect trust effectively? And are there any situations in which we can ignore direct trust? Intuitively, a truster should combine direct and indirect trust in such a way that over time, the role of direct trust grows with the number of interactions the truster has had with the trustee. And in this study, we would like to check if it's the case and if the influence of direct trust should grow with the number of interactions. To answer our questions, we designed a broad empirical study. Here you can see different methods that we use for combining direct and indirect trust. Three of them are novel, I mean the red ones, and I'll explain each of them briefly. The first one is the average of direct and indirect trust values is a straightforward approach. The second method is the online learning method. In this method, we consider direct and indirect trust as two experts, and then their weights are updated iteratively using the ITIA algorithm. The direct as advisor method uses a chosen indirect trust method and treats direct trust as if it were an additional advisor. So direct trust is not distinguished from other advisor, except that it's always honest. In the next method, we use an exponential function to compute the weight of indirect trust. Actually, it's a method of exponential decay of the weight of indirect trust over time. And here, P plus N is the total number of past interactions between a truster and a trustee. The ACT model uses a combining method based on reinforcement learning. So in our experiments, we incorporate the ACT method also in other systems to see how it performs. We also evaluate a system using direct trust alone and then indirect trust alone. Actually, this is a baseline to test if combining trust sources actually leads to improvement. In our simulations, we compute direct trust again using the beta reputation formula. And the four methods that we use for computing indirect trust are ITIA, Travis, MET, and ACT. Also, we have 14 settings which differ in how advisors can distort their recommendations. And we report simulations with 4 different percentages of deceptive advisors. Here, the evaluation metric is RFU, and our study uses 10 trustees and 10 advisors. We ran each of the indirect trust method in combination with every method for combining trust sources for each advisor setting. And we have a number of interesting observations. First of all, it turns out a system using direct trust alone is in most cases inferior to a system combining direct and indirect trust information. Also, weak indirect trust method like ACT in our experiments can improve significantly by using direct trust. But the best methods for computing indirect trust don't benefit from incorporating direct trust in decision making at all. And this is because the fact that by the time direct trust has become reliable enough, the indirect trust computed by these methods is as reliable as direct trust. And this makes direct trust redundant. Direct trust tends to be more beneficial in cases when all advisors are dishonest or when many advisors change their behavior dynamically. And actually, there are so many attack scenarios in the literature that advisors have dynamic behavior. So we can't ignore direct trust in general. Also, we show that the exponential function method for combining trust sources outperforms all tested methods. And by combining ITIA and the exponential function method, we can have a system that is highly robust across the wide variety of scenarios we tested. As a conclusion, we provided the first systematic study on when and how to combine direct and indirect trust. Based on our analysis, the best indirect trust methods benefit from incorporating direct trust only in certain scenarios, especially when advisors change their behavior dynamically. And also, one of our proposed methods for combining trust sources, the exponential function method dominates all other tested methods. And we also identified a robust system by combining ITIA with the exponential function method. This work has been published in ICHGAI 2020. So far, we assume that trustee behavior follows a stationary model. But in reality, this assumption often does not hold since trustees may change their behavior over time. And we call such trustees dynamic. One of the early efforts on the problem of dynamic trustees is to improve the beta-based trust models by adopting a forgetting factor. In this technique, older outcomes are assigned less weight than more recent ones. Although this approach shows success in specific scenarios, but it's not effective when trustees have highly dynamic behavior. Or for example, when a dynamic trustee, or in scenarios when a dynamic trustee acts with high trustworthiness for a certain amount of time to earn trust, and then suddenly switching to a low trustworthiness. This scenario is called camouflage attack in the literature. The other main technique to handle dynamic trustees is to use hidden Markov models or HMMs. In the HMM-based trust models, a trustee's behavior is represented by a certain state with a particular probability distribution over possible interaction outcomes with that trustee. And the trustee can change their behavior by transiting between states. Also, here we have some challenges. Some studies show that the HMM-based trust models can handle dynamic trustees better than the beta-based one with a forgetting factor. But the simulations presented in these studies are not comprehensive enough to evaluate the performance of these methods fully. For example, in one of these studies, all the tested scenarios are applied to a single trustee. Also, an HMM-based trust model is more complex and has more parameters than a beta-based one with a forgetting factor. Another major issue here is data sparsity when there are not enough interactions to train an HMM model. So we propose to extend better reputation system, I mean BRS, with the Page-Hinkley test. The PH test is a well-known change detector in signal processing. The original PH test is designed, is a two-sided test to identify both decreases and increases in the mean of a data stream. But since we are interested in detecting harmful changes in the behavior of trustees. I mean, when the trustworthiness values of trustees decrease, here we use the one-sided version of the pH test for finding decreases. The pH test has two parameters. The tolerance parameter, which indicates the allowed magnitude of changes, and the threshold. The value of threshold actually depends on the acceptable false alarm rate. We call our algorithm BRS-PH, and you can see the steps of this algorithm in this slide. Actually, we have a set R of trustees that are either aesthetic or not harmful. In the beginning, we assume that all trustees are static, and we put them in set R. We have a pre-processing phase. Actually, we use this step to get the initial estimates of trustees' trustworthiness. After that, for each trustee, the pH test is applied to the full interaction history to check if there are any harmful changes in the behavior of trustees during the pre-processing step. If such a change is detected in a behavior of a trustee, the algorithm removes that trustee from set R. Then in each round, a truster estimates the trustworthiness value of each trustee in set R, and it chooses a trustee with the highest trustworthiness value. Then based on the interaction outcome, the interaction history between the truster and the selected trustee is updated. In the last part, the updated interaction history is checked again using the pH test to see if there is any harmful changes in the behavior of the selected trustee. We compare BRS-PH to the methods the basic BRS with a forgetting factor, an HMM-based trust model, and also a method called RAP-TAR. To the best of our knowledge, this method is the only existing method using such like a statistical test for detecting dynamic trustees. In our simulations, we have 5 types of dynamic behavior. I already explained about the camouflage scenario in which a dynamic trustee behave honestly for a certain amount of time to earn trust, and then it starts to behave badly. Or for example, in the periodic behavior, a dynamic trustee alternates between honest and dishonest behavior periodically. And our evaluation metrics here are RFU and MAE. Generally, based on our results in terms of RFU, BRSPH is outperforms all other tested methods, and also in terms of MAE, it outperforms BRS with the forgetting factor, an HMM-based trust model, and the RAPTAR model. And there is no clear winner between BRSPH and the basic BRS. If you're interested, you can find the detailed analysis of the results in our paper. But one point here is that previous literature claimed that the HMM-based trust model performs better than the beta-based one with forgetting factor for handling dynamic trustees, but our results don't support this claim. And this work got accepted in Canadian AI conference. Okay, let's review the topics that I covered in this talk. We propose ITIA, a very simple and effective method for computing indirect trust, which scales well both in terms of memory and runtime. We showed the importance of studying utility-based measures. Also, we provided the first systematic study of combining direct and indirect trust. And we showed that the exponential function method is an effective method for combining trust sources. And by combining ITIA and the exponential function method, we can have a robust and effective trust system. Also, regarding the dynamic trustees, we propose to extend BRS with the Page-Hinkley test. It's a simple approach, but it's still effective. Yeah, thank you. Any questions?
Thanks, Elham. If you have any questions, please feel free to unmute yourselves and ask directly. Otherwise, you can type in your questions in the chat box and I'll read those to Elham. Okay. I guess if there are no questions, we can just thank the speaker. Thanks, Elham, for volunteering today for today's AI seminar. And we will see everyone next week. Stay safe.